Hey boys, section 2 here, we're just going to go through a bunch of different properties of radicals, how to manipulate them, simplify them, rationalize them, things like that. All right, the first one's the product rule. The product rule is the way that we break down radicals and simplify them. Okay, so what you need to do is you need to find basically perfect roots within whatever we have. Okay, so for this one, we've got, we want to take the fifth root of 64. Okay, so we're going to break down 64 into some roots that are perfect roots that we know. Right? So we know that 64 is 2 to the 6th. You might not know that, but you can mess around with it. 2 is obviously an easy one to start with when you're trying to find perfect roots. Okay, so it's the same as 2 to the 6th. Right? But 2 to the 6th we know is also the same as 2 to the 5th times 2 to the 1st. Right? 2 to the 6th is equal to 2 to the 5th times 2 to the 1st. Okay, so if you write it like this, you suddenly see here that the fifth root and the 5 exponent are going to cancel each other out. And so this could simplify to 2 times the fifth root of 2. Okay, that's how we simplify those. All right, an easier one here, I think, number 2, right, because we have squared. All right, so we got to take the square root of 18 breaks down to square root of 9 times square root of 2. 9 times square root of 2. Okay, and the square root of m cubed can break down to square root of m squared times the square root of m. So we've got a couple perfect squares in here, which that we know. All right, so square root of 9 we know is 3, and square root of m squared, we know those cancel out, and we're left with m. So we'll have 3m on the outside, square root of 2m on the inside. That's the broken down, simplified version. Okay, now quotient rule, right? You could break up a fraction, a square root of a fraction, to square root of the top, or not square root, the root of the top divided by the root of the bottom. Right? But remember that you cannot have a root in the denominator. Okay, so in order to get rid of the root of the denominator, you got to multiply the top and bottom by that root to get rid of it. Let me show you. So we've got the cube root of 5/4. We change to cube root of 5 over cube root of 4. Right? Neither of those are perfect, right? But we know if we multiply this bottom by the cube root of 2, then we'll have the cube root of 8, which we do know. Okay, so let's multiply the top and bottom by cube root of 2. Okay, so we'll be left with, right, cube root of 5 times 2 is cube root of 10. In the bottom we have cube root of 8. Right, and the cube root of 8 is 2, so we've got cube root of 10 over 2. All right, second one. This one we can break down as well. Right, split it up top and bottom. You can write it, you don't have to. But we know that the top is 3 to the 4th, right? 81 is 3 to the 4th power. So if we have the cube root of 3 to the 4th power, and we know the cube root of 8 we just did is 2, we could still simplify this top because we could pull out 3 of those 3's. Okay, so we've got 3 cube root of 3 over 2. That's the final one. This is a little tricky one that is more helpful if you don't have access to a calculator. Because obviously you could just type this into your calculator. But for this one right here, you can simplify this by recognizing that whatever's on the outside here could be 2 numbers multiplied by each other. Right? And if it is 2 numbers multiplied by each other, you could just separate them and create 2 different roots. Okay, so we could recognize, we know that 169 is a perfect square, right? 13 squared. So we could rewrite this as the square root of, right? Because square root of, we assume it's a 2, the square root of 169. Okay, now the reason you'd write that is because now we see that we've got, right, we know that 2 times 2 is 4, so these are equivalent to each other. Okay, but we know the square root of 169 is 13, so this is really the same as the square root of 13. Okay, and then you can leave it just like that. All right, that's just another helpful way to do this. This theorem 2 is, again, more for being able to do things without a calculator. But if you have something like this where you have an exponent on the inside of your root, okay, you could rewrite it as finding the root first and then take the exponent. Now the reason you do that is because if you square it first, you're just going to get a giant number, which you're not going to know the root perfectly for. So to simplify it, we'll take the root first to give us a smaller number that we can handle, and then take that to the exponent. Okay, and this is probably a good time for me to mention, if you're typing this stuff in your calculator and you have something like this, okay, this is the same as the way you type this in your calculator is b to the m over n power. Okay, so this exponent on the inside is the numerator of your fraction. The exponent on the index is the denominator. All right, so for 216 squared, the cube root of 216 squared, right? The way you type in your calculator, if you just want to do it that way, is 216 to the 2/3 power. Right? Now, if you don't have a calculator, you can still solve this pretty easily. Let's rewrite it as the cube root of 216, and then square that. Right? So we get a smaller number that we'll know. Now, the cube root of 216, you may or may not know it. It's 6. Okay, so 6 squared is 36. That's the final answer. All right, this is started the examples because I did like 1,000 of them. But they're all pretty quick. We're just simplifying stuff as much as we can. So we've got 5 root 24 times 3 root 8. All right, the first thing I'm going to do is I'm going to combine these on the outside and combine these on the inside. Okay, so we've got 5 times 3 is 15. And on the inside, we've got a root 24 and a root 8. Well, I want to get 2 8s in there, right, if possible. So I can rewrite this as root 24, we can write it as 3 times 8 and leave the 8 in there. Okay, so since there's 2 8s in here, that's like 8 squared, so the 8s can come out to the outside, because this would be rewritten as 15 times 3 times 8 squared, right? And 8 squared is obviously, or square root of 8 squared is obviously 8, so these would cancel. And we'll be left with 15 times 8, I need more space, root 3. Okay, which you could simplify even further to 120 root 3. Number 2 here, we just have a fraction that, or a radical in the denominator. We got to get rid of that, so we have to rationalize this by multiplying by 5a over 5a. Right, so root 5 over root 5a. So on top we'll be left with 12 root 5a. And on bottom, root 5a times root 5a are going to cancel, right, the radicals, and we'll be left with just a 5a on the bottom. So we're going to continue on powering through these examples. We've got a whole bunch here at the beginning with just square roots, because we're kind of familiar with them and they're pretty easy, and then we'll get to the harder higher roots one after that. So if you could simplify them like this, you could simplify them with the higher roots as well. So start by breaking down root 75. Okay, remember, just use the product rule. Okay, so find a perfect square that's in there so we can pull it out. Right, so rewrite this. Right, the biggest perfect square that's a factor of 75 is 25 and 3. Right, which one of those do we know? We know a square root of 25 is 5. So this is 5 root 3. So the fraction one, right, remember we split it? Root 8 over root 25. This one's nice and easy. Right, we got to simplify the top. We know that root 8 is the same as square root of 4 times square root of 2. Square root of 4 is 2, so this is 2 root 2. And on bottom, square root of 25 is 5. So square root of 2 over 5. That's just not even close. I apologize for not being able to write. Number 5. We have to be able to rationalize the denominator, right? Can't have the square root in the denominator, so to get rid of it, multiply by square root of 3 over square root of 3, because that's going to get rid of our roots on the bottom. And we'll be left with 15 root 3 over 3, but you could simplify 15 thirds to 5 root 3. All right, number 6, we've got 9 root 5 over 27. Okay, for this one, the 9, you're just kind of going to hang out with it for now. Split our radical, root 5 over root 27. All right, the 9's really going to go at the top, so you can start thinking of it that way. The root 27, you probably want to break these down first. Okay, so let's do 9 root 5 on top, because root 5 you can't do anything with, it's prime. And root 27, the biggest perfect square that's a factor of root 27 is 9. So rewrite this as square root of 9 times 3. Square root of 9 we know is 3. So we've got 9 root 5 over 3 root 3. Okay? Now, a couple things need to happen. We need to simplify the 9/3, and we need to multiply the whole thing by root 3 over root 3 to get rid of our radical here in the denominator. Okay? So simplifying 9/3, we've got 3 on top and 1 on bottom. We have a root 15 on top now because we have root 5 times root 3. And on bottom, we'll have a root 3 times root 3 is 3. So those will cancel out, and we'll just be left with root 15 as the final. Number 7, here's where we'll get to cube roots and do a little bit more with them. All right, so the cube root of 1/4 is equal to the cube root of 1 over the cube root of 4. Cube root of 1 we know is 1. Okay, so 1 over the cube root of 4. Now cube root of 4 we can't have in the denominator, so we got to get rid of it. Well, we know that 4 is same as 2 squared. So we really only need to multiply the top and bottom by 1 more cube root of 2 in order to get rid of that radical in the denominator. So multiply by cube root of 2 over cube root of 2. Okay, so now you're going to have cube root of 2 on top. Oh, that's not right. Whoop. Cube root 2. And on bottom, cube root of 4 times cube root of 2 is going to be the cube root of 8, and cube root of 8 is 2. So that is our final. Number 8, we've got the fourth root of 162. So if you had a fourth root of something like this, I would check just to see if this on the inside is a perfect square. Because if this is a perfect square, like, for example, 144, then you could use that double square root thing, right? You could do the square root of 144 of square root of 144, right? But it's not a perfect square. 162 is not a perfect square, so that's not really going to help us. All right, what we have to do is we have to start breaking that down and figure out what perfect fourth roots are in there. Well, I suggest we start with 2, right? 2 to the fourth is 16. Does 16 go perfectly into 162? No, it doesn't. So let's try 3 to the fourth. 3 to the fourth, you can type in your calculator. If you don't know it, is 81. Does 81 go perfectly in there? Yeah, it does. So this is, oh, I need to change my thing. Okay, so this is the fourth root of 81, which is 3 to the fourth, times 2, right? 81 times 2 is 162. So 3 to the fourth is going to come out, and we're going to have 3 times the fourth root of 2. That'll take some practice for you to get used to, but you can handle it for sure. Now, number 9, we've got the fifth root of 3 over the fifth root of 32. Well, the fifth root of 3 you can't do anything with. Fifth root of 32 is 2. So that's it. Now, the square root of 3 times the square root of 15. This one, also pretty easy. It's just the square root of 45. Multiply those together. Okay, square root of 45, biggest perfect square that goes in there is 9. Square root of 9 is 3, so 3 root 5. Number 11. Number 11, so we need to break this down first. We've got cube root of 2 over the cube root of 9. Remember that 9 is 3 squared, so we can think about, we just need one more 3 in the denominator. And we're multiplying this thing by 3 times the cube root of 4, which is 2 squared. Okay, that'll be helpful because now we recognize, right, it's like that over 1. We recognize that we have perfect on top, so we've got 3 times 2 because we'll have the cube root of 2 cubed when you combine our cube root of 2's on top. So if 3 times 2 is 6 on top, times the cube root of 3 squared on bottom. To rationalize that, you just got to multiply top and bottom by a cube root of 3. And we'll be left with the 6 times the cube root of 3 over 3, which is 2 cube root of 3. That's the final. All right, last problem. 10 root 5 or 5 root 2. If you have something like this, okay, we can obviously simplify these, and then we have to multiply top and bottom by root 2 over root 2 to get the root 2's out of the bottom. Okay, so 10 over 5 just becomes 2 over 1. 5 times 2 is 10. And root 2 times root 2 is 2. Those cancel out. You're just left with root 10. That's it, gentlemen.